When we are looking at single replacement and double replacement reactions, there's a certain set of conditions that have to be met in order for the reaction to actually take place. We talked about how sometimes you can have two chemicals put together that actually don't react together, and we say it's no reaction. So when we're talking about a single replacement reaction, that's whenever you have your one element that bumps out or replaces another element that's in a compound. And like elements will replace like elements. You have metals that bump out metals, or you can also have hydrogen in that same place because it takes the role of the positive ion. And then you, of course, have nonmetals bumping out nonmetals. Anytime we're working these sorts of reactions, remember we do need to watch out for our diatomic elements, the hydrogen, iodine, bromine, oxygen, nitrogen, chlorine, and fluorine. Hi, Broncliffe. And we will find our charges for ionic compounds. And we will not carry over subscripts unless they're part of a polyatomic ion like NO3, PO4, SO4, things like that. So in order for us to know whether an element has the strength to bump out another element, we're going to be using a resource called the activity series. And when you're looking at nonmetals, oftentimes you may not even be given a list of these because they're just the order that they're on the periodic table. So fluorine is the top halogen, so it's going to be the strongest, and it's going to be able to kick out and replace any of those that are below it. Iodine is going to be the weakest, and it is not going to be able to replace anything. It will be no reaction if it's combined with a compound that has any of those up above it. On the right-hand side, you have an activity series for our metals, and that's going to include hydrogen there because it is taking the role of the metal in the ion. It's the positive ion. And up here at the top is going to be where it's the strongest. You can see the arrow along the side that says we have increasing activity as we travel up the table. And so those are going to be stronger at the top. And then down here at the bottom, gold is going to be the weakest. So as long as an element is above another element, it can kick it out and take its place because it's stronger. So when we take a look at our first example here, we have K, potassium, trying to react with copper chloride, CuCl2. First of all, we need to try to figure out what element the potassium is going to try to replace. So we need to know whether potassium is a metal or a nonmetal. So when we look it up on the table, it's in the very first column, and it's going to be an alkali metal. And so we need to find the element in the compound that's like it to see what it's going to replace, or try to replace. So copper or chlorine, copper is going to be our metal. So potassium is going to try to replace copper, kick it out and take its place. So we go to our activity series and see if potassium is strong enough to do that. So we go and we find potassium here. And copper is, I don't even see it on there yet. It's all the way down here. So compared to potassium, copper is very weak. And so whenever potassium comes and tries to take its place, it can. It can kick out copper. Copper is left right here by itself. And now the potassium and the chlorine are free to pair up. And I'm not going to put the 2 on chlorine because remember, subscripts do not get carried over unless they're in a polyatomic ion. We need to look at the charges of potassium and chlorine to see how they're going to come together. So potassium is +1, chlorine is -1, so we are going to use just one of each. Okay. Now this is not a balanced equation. So let's go ahead and make sure that we get it balanced. We have too many chlorines on the left-hand side. We have 2 of them and only 1 on the right, so we'll put a 2 right there. That gets our chlorines balanced. But now they gave us 2 potassiums on the right-hand side, so I'm going to come over here to the left and put a 2 in front of potassium. And then I have 1 copper on each side. So in our blanks, we're just going to fill in ones. And now it's a balanced equation. And if you want to put a little note underneath here for what we actually looked up on our table, we looked to see can potassium, can K replace Cu? And yes, we saw that it can. And the reason why we were trying to replace Cu is because that was the metal and potassium's a metal. Okay. And we'll go ahead and circle those. Okay, let's try another one. We have aluminum nitrate and magnesium, and we want to see if this reaction will actually happen. So let's go ahead and write this as a formula. So we're going to have positive 3 for aluminum, negative 1 for nitrate. It's a polyatomic ion. So we're going to have AlNO3, but we're going to have 3 of those nitrates. And it's going to react with magnesium. It has no charge because it's a single element. We just have to think about, is it diatomic? Does it need a 2 after it? And it is not one of those high Broncliffs up at the top, so it does not get a 2. And then we look and see what the single element is. The single element is magnesium. And when we look it up, it's to the left of the staircase in the second group, so it's a metal. So that means it's going to try to replace the metal that's in the compound. So between aluminum and nitrate, metal will be aluminum. So we're going to go to our activity series and we're going to look up aluminum and magnesium. Okay, so I'm looking. We've got magnesium and aluminum, one right above the other. So think about which one is stronger. Magnesium is above, so it's going to be stronger. So magnesium can kick out aluminum, but not the other way around. And magnesium is trying to kick out aluminum, so it's good. It can react. And so you're going to put a little note down here that you're trying to figure out, can magnesium replace aluminum? And we saw that yes, it can. So it kicks it out. Aluminum is all by itself. And now magnesium and nitrate pair up. We're going to go ahead and just start with one of each. And then we have to look at the charges. Magnesium's +2, nitrate's -1. So that means that you're going to need 2 of those. And it is not balanced. If we look at our nitrates, we have 3 on the left-hand side and 2 on the right-hand side. So anytime you have 3 and 2, remember you have to make them both equal 6. So we're going to multiply this one by 2 and this one by 3. That gives us 3 magnesiums right there, and it gives us 2 aluminums. Okay. Let's try another one. We have barium fluoride, +2, -1. And it's reacting with iodine, has no charge, it's by itself. And we're going to see if that reaction will take place. So we're going to have 2 fluorines paired up with our barium. And iodine's by itself, so it's just I. But we check to see if it's diatomic, and it is, so it gets a 2. And then we need to see if our single element, which is a nonmetal, can replace the nonmetal in the compound. So we look up barium and we look up fluorine. And fluorine is the one that's on the right-hand side of our staircase. It's the nonmetal. So iodine is going to try to replace fluorine. So can iodine replace fluorine? So we go and we look at our activity series, but we have to make a note that this is non-metal now. So we're actually going to look at our list right up here. And is iodine strong enough to replace fluorine? Iodine is down here. Fluorine is the strongest. So is iodine is the weakest going to be able to kick out the strongest one? No. Iodine cannot kick out fluorine. So instead of actually writing products that aren't going to form, we're just going to put no reaction. Because no, it could not replace it. Okay. Solid copper 1 iodide reacts with chlorine gas. +1, -1. Chlorine, no charge because it's by itself. So we've got copper and iodine, one of each because it's +1, -1, reacting with chlorine. It's diatomic. And the chlorine, which is our single element in a nonmetal, is going to try to replace the nonmetal in our compound. So can chlorine replace iodine? So we look and see, is chlorine stronger than iodine? So now we're looking at these two, and chlorine is stronger than iodine, so it can kick it out. So it kicks out iodine, so it's all by itself. And iodine is a single element. It's diatomic. It gets a 2. And now the copper and the chlorine are free to pair up. So we'll go ahead and just write one of each, and then look at the charges. Copper, they told us in the problem, has a charge of 1. Chlorine's going to be -1. So it's good like that. We don't need any subscripts on that. But if we look at the overall equation, we can see it is not balanced. The chlorines we have on one side do not match the chlorines on the other. Same with the iodine. So if I'm going to balance the chlorine, I'm going to put a 2 there. And that means we need 2 coppers. So I'm going to put a 2 there, which gives me 2 iodines, which I already have. And my chlorine balances out. So now it's a good balanced chemical equation. Now, instead of looking at a single replacement reaction, if we're going to look at a double replacement reaction, which is whenever 2 elements from different compounds switch places, we will need to find charges. There will not be any single elements, so we don't have to worry about if they're diatomic or not. And we're still going to follow the rule that we're not going to carry over subscripts unless a polyatomic ion is involved. And there are 3 things that could cause a double replacement reaction to occur. We could have the formation of a gas. We could have the formation of a molecular compound like water, carbon dioxide, things that don't have charges. Or, and the one that we're going to focus on the most, is the formation of a precipitate. And a precipitate, remember, is that solid that forms in a chemical reaction, and it's going to make it look all cloudy. And we have another resource we can use to figure out if that will form. We call it the solubility chart. Solubility just means dissolving. So if something is soluble, it means that it can dissolve. If it is insoluble, it means that it cannot dissolve. And we have some symbols that we're going to use to designate whenever we have a precipitate. When we're going to use a down arrow, because whenever that solid forms, it kind of falls down to the bottom of the container. So we're going to use a down arrow to show that we have a precipitate. And if it does not dissolve, if it does dissolve, if it does not form a precipitate, that means it's soluble. And we're going to show that it's soluble by using the abbreviation AQ. And what that stands for is aqueous. And that just means that it's dissolved in water. Okay. So we're going to use our solubility chart, which is on the back of your note packet, to be able to figure out if a compound will be insoluble, which means it will form a precipitate, or if it will be soluble, which means it dissolves and it does not form a precipitate. So we look up NaCl, and on our solubility chart, you'll notice that all of the ions that are listed are the negative ions, except for the second one from the top here, ammonium. Okay? All the others, we just care about the negative ion, the second thing that's in the compound. So whenever we look at our first example here, we have NaCl. So what we're really concerned with is looking at Cl. And we're going to look and see, is it in the section that says soluble, or is it in the section that says insoluble? So we look up Cl, and it is right here. And so if it's bonded with Cl, it's soluble. It will dissolve. If you want to put a little note here, that means it's going to dissolve. Unless it's with silver, lead, or mercury. If it is bonded with one of those 3 things, that kicks it into the other category. It means that it will form a precipitate. It will be insoluble. But we have NaCl. Na is not an exception we have given, so that means that our chlorine here is soluble. We just look to see which category it's in. So we're going to put that it's soluble. And so that means that if it's soluble, it does not form a precipitate. And so if we were going to be writing a chemical equation and show that this does not form a precipitate, after it we would write a Q. So the next one we have is AgCl. So again, we're going to look up chlorine. But you'll remember that one of our exceptions was silver, which is what we have now. So whenever we go and look at our solubility chart, whenever it is on the exception side, it bumps it into the other category. So because it's bonded with silver here, that bumps it down, and it's going to be insoluble. So we'll write insoluble. And that means that it will not dissolve. It does not dissolve, and it will form a precipitate. So that means that if we were writing the equation, after the formula, we would put a down arrow. Okay, the next one, we actually have two different ions we could look up. We could look up NH4 plus or PO4 3 minus. So we can go for this one or this one. If we look up NH4 plus, you'll see that it is soluble, and there are no exceptions. It is soluble always and forever. So there are certain things that you'll see often enough, especially that one and nitrate right below it, that they will always dissolve. There's nothing you can put them with that they will not dissolve when you put them in water. So it is soluble. You just look up there to see what the name is or what type of reaction we'll see. And since it's soluble, it will not form a precipitate, and it will be aqueous, dissolved in water. If we looked up the other ion instead, the PO4 3 minus, we would see that the phosphate is actually not in the soluble section, it's in the insoluble section. However, its exception is whenever it's with ammonium, which it is. And so that bumps it up into the other category. It will also switch categories if it's with an alkali metal cation, and you'll notice that almost all of these down here have that as an exception. And what that means is that it's in group 1. So that's going to be things like lithium, sodium, potassium. Okay? All of these, and there are more in that group, but those are the main ones, will switch it into the other category. Okay, our next one here is barium sulfate. So we're going to look up the sulfate ion and look and see its solubility. So we're looking up sulfate, SO4, and it's right here. It's going to be soluble unless it's with strontium, barium, lead, or mercury, which we saw that we're talking about when it's bonded with barium. So that kicks it to the other category. It now becomes insoluble. So we'll fill that in. And when it's insoluble, it does not dissolve. It will form a precipitate. And we show that with a down arrow after the formula. Okay. So we've got NO3 for our negative ion, NO3 minus. And it's bonded with copper over here. So let's go and find NO3. Nitrate is soluble always and forever. There are no exceptions. So since it's soluble, it dissolves. There's no precipitate. And since it's dissolved in water, it is aqueous. So let's see how we would actually write this with an equation. So we have aluminum chloride and silver nitrate reacting, and since this is going to be double replacement, we know that we're going to have the metal from one and the non-metal from the other pair up. So I'm going to go ahead and leave a space here for balancing as we go. So we're going to have aluminum and nitrate. And I'm going to go ahead and just write one of each because we need to look at the charge then to balance the compound. So aluminum's +3, nitrate's -1. So we're actually going to need 3 of those. And then the two inner elements are going to come together. And we always write the metal first. So we're going to have Ag paired up with Cl, and it's a +1 -1, so the compound is balanced. So now we need to check and see if this reaction will actually take place. So we need to look up our negative ion here. So we're going to look up nitrate and chlorine. So let's go and look those up and see where they fall. So nitrate is going to be soluble always. So next to nitrate, next to that compound, we're going to end up putting Aq. It's aqueous. So far, we're not having any indication this reaction will actually happen. We have to have a precipitate form in order for the reaction to take place. So we need to look up chlorine then. So we look up chlorine. We've got Cl right down here. It's also soluble unless it's with silver, lead, or mercury, which, if we go and look, we were dealing with it whenever it's bonded with silver. So that means that it's going to be an exception. It moves it into the insoluble category, and so this is our precipitate. So we draw the down arrow after that to show that that's the precipitate that's going to show the reaction is happening. And then after this one, we're just going to put a little Aq. So since the reaction will happen, we'll go ahead and balance it. We look and we see that the nitrate is not balanced. We have 3 on the product side, so let's put a 3 over here to make it match. Now we have 3 silvers, 3 Ags, so we'll put a 3 over here. That gives us 3 chlorines, which we started with 3 chlorines, and then we have an aluminum on each side. So we have a nice balanced equation now. Okay, one more. A yellow precipitate is formed. So we know the reaction is going to actually happen. It tells us a precipitate is formed. When an aqueous solution of potassium chromate, so potassium chromate is +1 -2, and it's mixed with an aqueous solution of lead-2 nitrate. So lead and nitrate. And the aqueous part, again, just means it's dissolved in water. And when you have a double replacement reaction, both of your reactants will actually be dissolved in water. But we're going to go ahead and write our skeleton equation, but leave spaces so we can balance. We're going to have K2, and then chromate is CrO4. That's a single chromate. So we're going to have one of those attached to the 2 potassiums. And then we're going to react that with our lead-2 nitrate. So we have Pb, and then we're going to need 2 of these nitrates. And we have to figure out what the products will be. So we take the 2 outer parts, which this is a polyatomic ion here, so we're going to take it as a whole thing. And we're going to have KNO3. And we just write one of each until we can check out the charges. Potassium's +1, nitrate's -1, so it's actually good like that. And then the other product that could form would be between barium and then our other polyatomic ion here, the chromate. So we're going to have PbCrO4, and we'll check and make sure our charges work out. We have +2 and -2, so it's good like that as well. And then we have to look and see which one of those things will actually be our precipitate. So we're looking up NO3 and CrO4. So we go and we look up NO3, which we had before, and it is aqueous. It is always soluble, no precipitate. The other one we were looking up was CrO4. So we're looking, there it is. Chromate is insoluble unless it's with ammonium or any of our alkali metals, the sodium, lithium, potassium, things like that. So let's look and see what our chromate was with. Our chromate was with lead. Lead was not one of those that we mentioned. So that means that this is our precipitate. We put the down arrow after it, and this was aqueous. It dissolved in water. So because this was a precipitate here at the end, this last one, that means that the reaction will take place. We need to go ahead and balance it then. So we look and we see that the nitrate is not balanced. So we'll put a 2 right here, which gives us 2 potassiums, which we already have, and just that one coefficient balanced the whole thing. Now, if you were looking at a double replacement reaction and both of your products ended up being aqueous, neither one of them formed a precipitate, that's when you would just cross out both of the reactants, or not the reactants, both the products that you said could possibly form. You just cross them both out and you put no reaction, just like we did when the single replacement one didn't react. And at that point, you don't have to balance anything because you're already saying that it's not going to happen.